Good morning. So, we'll be starting our next unit of mechatronics, that is unit number 3, time domain and frequency domain analysis. So, we have finished with unit number 1, 2, and 3. So, in unit number 3, we have left out this last, unit number 2, we have left out this last portion. So, that we'll be going to cover in the practical session as I have earlier conveyed to you. The next will be starting unit number 4, which is time domain and frequency domain analysis, in which we'll be going to discuss what is the effect of unit step response via transient response specifications. And these are the specifications like percentage overshoot, rise time, delay time, steady state error, etc. These are the things that we'll be uh, discuss in due course of time just when we proceed further. Also, we have the frequency domain analysis. So, what is frequency domain? Parameters are there. It is natural frequency, what is damping frequency, and what is damping factor. That we'll study in detail, and we'll discuss how to map the pole zero plot, that is the S-plane graph with the damping factor, natural frequency, and along with the unit step response. We'll be going to discuss what is Bode plot. It's one of the diagram which is used to for the analysis of your control system, and then we'll discuss what is gain margin, what is phase margin, etc. So these are the things that are included in unit number 4. So let us start unit number 4. Let me open the presentation. So, so far we have discussed till now that we have now know what is the transfer function, and what is the significance of the transfer function, that we know. Also, we know that how to combine the individual transfer functions, and how to convert it into a single transfer function using your block diagram reduction method. And also, there is one technique called as signal flow graphs, but that is not included in the syllabus. But with the help of block diagram reduction, we know how to reduce a control system into a single block. Now, in this unit, we'll be going to discuss how these blocks respond to the different input. So we know that if we have a block like this, inside this block we have a gain, or we call it as a transfer function, and we have input like R of S, and we have output like C of S. So what will be what is this, how this block responds with the different type of inputs. Okay, what does it means? We'll be now going to take the closure loop at the response characteristics of the system. What we'll be going to do, what we are interested in, to find out the response characteristics of a control system which is under consideration. So this is the main objective of the this unit. Now, there are two ways like time response and frequency response. So first, we'll be going to discuss what is time response of a system. Now, time response of a system is defined as output of a system when it is subjected to input of a system when it is subjected to an input. Now, this input is a function of time. This input is a function of time. That is what we call as time response. Response is your output. What is response? It is a kind of output of a system when it is subjected to certain input, certain stimulus. Then the input is such that which is a function of a time. Now, when this function of time input is subjected or sent given to a system, whatever the response that we'll be getting or output we'll be getting, that is called as time response. Now, time response analysis, the meaning of this is subjecting a control system to the inputs that are the functions of time and studying their outputs or responses which are also a function of a time. Now, when this input is a function of time, whatever the outputs or the responses that we'll be getting, those are also the functions of time. Okay. Now, a control system which generates an output or response for a given input, that we know. Whenever a control system is given an input, it will provide the output. Now, let us take an example of an elevator, the lift that we use in our apartments. Very interesting example. When some person enters into the lift or an elevator and he presses the 11th floor button in the lift. Now, that 11th floor button, after pressing, that is your input to the system. Whatever the floor number button he or she is pressing, that is input to the system. Now, what happens after that? The motor of the elevator starts moving. Whatever the motor is installed, that motor starts moving or it starts rotating, keeping the cart in a or moving the cart in the upward direction. Now, in the interest of passenger safety, we should not like that the elevator should give a sudden response and shoot off to the 11th floor. So is it happening? We have pressed the button and suddenly the within a few seconds the elevator moves to the 11th floor. So it is not desirable because of the passenger safety, interest of the passenger safety. It will be hazardous to the passenger. Now, what instead of what we would like to prefer, that the elevator must reach to the desired floor in a smooth manner. Now, other important thing that we should note that the elevator should come exactly the alignment with the reached floor. Okay, we don't like that the floor the elevator is stuck between the two floor. Like we have to reach 11th floor, and if it is stuck between 11 to and 12th floor, that is also not desirable. So what are the two specific requirements in case of the elevator when we consider the passenger safety? The two important specifications are the should gradually elevator should gradually rise to the desired floor. Desired floor. That is the one requirement. Second requirement is it should stop exactly at the desired floor. It should stop exactly at desired floor. So these are the two specific requirement that we consider in case of the elevator. Now you know what is the case. Now let us see the different responses of the for this control system. Okay, with respect to time. I'll explaining these responses along with the graph. So on y-axis we have a floor number. We have to reach at 11th floor. Okay, and on y-axis we have a time. Now the first response, let me draw this dot line. So this is a response like this. So this is 10.5 fifth floor. Now what is this condition? Now in this, if we see that the output rises gradually, very gradually, okay, and the elevator is extremely slow. Elevator is extremely slow. I can make this also like more slow like this. Okay, so it takes, the elevator takes lot of time to reach at the desired floor, and also it will not desire it will not reaching to the desired floor, but it is stopping at stopping in between 10th and 11th floor. So what is this response? The elevator elevator speed is very slow, and it stops between 10th and 11th floor. Okay, so this is one kind of response which is not desirable. Now let me draw another kind of response. Okay, so this is again a floor and this is time. So we have this 11th floor and this is 10.5 floor. So this is another response. Now what is the difference between these two responses? Now in this second response in figure B, we can see that although the response of elevator is faster than the previous case, which one is good, but again your elevator stops between 10th and 11th floor. So what is the second case? Response is good, but elevator stops in between 10th and 11th floor. So this is one response. Now let us see what is next kind of response. So this I want you to explain this response. I want any one of you to explain. I'll draw the response. So this is your 11th floor. This is your 12th floor, and this is your 10th floor. So what is this response? This is response number C. Can anyone tell me what is this response? Sachin, can you tell me what is this response? What is the speciality of this response? In this response, we can see that since this response is very fast, it is very fast, but it oscillates between 10th and 12th floor. So the first your elevator goes fastly to 12th floor, then it go back to 10th floor, and slowly it will come down and it settle down to the 11th floor. So although the response of the system is very fast, it initially it oscillates it initially oscillates between 12th and 10th floor, which is again not acceptable. And your last kind of possible kind of response is this one: time. This is floor, this is 11th floor, and the lift elevator goes like this. So this is your this D response is the best response. D response is the best response in which the elevator rises in a smooth manner and it will stop exactly at 11th floor. So these are the possible responses of the elevator that can be happen when supplied with certain input. Now, each of these four figures represents your time response of a control system. Whatever the diagrams I have drawn over here, diagram number A, B, C, and D, these figures represents the time response of a control system. In this case, it is an elevator. As said earlier, time response is the response of the control system, which is a function of time. Okay. Now let us move forward. Let us take the time response of let us say which one we take. We take this one, this B. Okay, B response. I'll once again draw this response. This is time. This is floor. Now we have over here 10.5 and we have 11th over here. So the elevator goes up to this and it stucks in between 10th and 11th floor. Now this is your input signal, and if I draw this, if I can measure this difference is your steady state error. So this is obviously an error because where we have to go over here and what we are achieving. So error is simple terms. Error is where we want to be and where we are. That is what we call as an error. In life also, I want to be a successful person or a good engineer, I should have a good job. That is what is input signal, what we expecting. But I'm not that competent to get that particular job. So where I am currently, so where I have to go and where I am, that difference is always there, whether you can talk of the control system or whether you talk of your life. So it is called as an error. And if it is remaining steady throughout your lifespan, it will be a steady state error. We call it as a steady state error. Now, this entire time response we can divide into two parts. This is your first part, and this one is second part. Now, in part one, your output is changing with respect to time. You can see over here. your output of the control system is changing with respect to time. But in case of the second part that we are talking about, in second part, your output is almost constant. Okay, like this. It is not changing with respect to time. This first part is called as the transient response. This first part is called as transient response. And this second part is called as steady state response. So there are two type of responses in time domain response. So in time response, this time response is subcategorized into two parts. This is called as first part is your transient response. So in transient response, your output is continuously changing with respect to time, while in steady state response, your output is not changing with time, it remains constant. It is more or less constant, we can say that. Now, we know that we can note that the output settles between your 10.5 instead of 11. That error is known as steady state error. We'll be talking more about this steady state or error as we progress. But time being, you remember, so if we are not achieving what is desirable and it is remaining, that undesirable condition is remaining for an entire lifespan, so that is called as error, that is called as steady state error. Okay, now if we talk of this diagram, so in this diagram where the system is oscillating, so this part is your first part, that is transient response, and after that your steady state error become zero. Also in this case, if we divide it, it is the first part transient response, and this is the second part, that is steady state response. So here also your steady state error is zero. So what we want the steady state error to be zero. By looking at these diagrams, we can say that the transient response may be exponential, as in this case, or it may be an oscillatory type of response. So we can sum up over here that your total time response for a control system is C of t, which is equal to your transient response. I denote it as Ct of t, which is a function of time, obviously, plus steady state response, which is also a function of time, but it is almost more or less remain constant. So transient response is a summation of the total time response is a summation of this transient response plus steady state response. Now again we'll be going to into detail, but let us spend some time on discussing the input signal, because when we get the input signal, then only we'll get the output. Now what are the types of inputs supplied to a system? Okay. Now for the analysis, time response analysis of a control system, we need to expose a system to various test inputs, then we can, that is the first step to start the analysis procedure, or specifically time response analysis. Now test input signal are used for testing purpose, how well your system is respond to your known inputs. That is the purpose of test input, to just identify, to get an idea how well your system is responds to your known input. It is not always necessary to choose the complex or some complicated input signal to analyze the system behavior. We can take a simple standard test signal for the analyst to analyze the system. Now, some standard test inputs are impulse input, step input, ramp input, sinusoidal input, and parabola input. Let us see one by one all these input. First input is your impulse input. Remember, these are the standard test input signal. Now, impulse represents the sudden change in input. What it represents? It represents sudden change in input. So we give a rapid input or impulse. That impulse is infinite at time t is equal to 0. This impulse is infinite at t equal to 0, and 0 where everywhere else. Okay, and let me write it, and 0 everywhere else. Let me represent this kind of input in the form of a graph. So this is your time on x-axis, and on y-axis I'll be putting an input. So this is what we call as an impulse input. This is an impulse input. So at t equal to 0, this value of input or the value of impulse, it is infinite. It can reach up to infinite value. But all other places like this, in these regions or in these regions, it is having a zero value. Now, if we talk of if this infinite impulse is a little bit impractical, so for that we go for the unit impulse. Now, what is unit impulse? This unit impulse is having magnitude of 1 at t equal to 0. So, if I say this equal to 1, this is equal to 1, this magnitude is 1 at t equal to 0. Now, I can write r of t, that is input delta t is equal to 1, okay, at t equal to 0, and at t is not equal to 0, the impulse input is 0. Everywhere else except t equal to 0, the value of impulse input is 0. Now if we take a Laplace of this equation, so we can write it like this: r of t, which is equal to Laplace of delta t is equal to 1. Okay, now impulse input, they are used to derive the mathematical model of a system. So these impulse inputs are used to derive mathematical model of a control system. This is what we call as an impulse input. Let us talk about second kind of input is step input. What is step input? This step input represents a constant command. It represents a constant command like a position. Now, if this input is given to an elevator, that is your step input. Another example, if we talk of, if we set the temperature of an air conditioner, so that is what we call it as a step input. In the diagram form, on the graph, I can represent this step input as, this is R of t and this is t. So this is your step input. It is like this. So this is your step input. Now, if we write in the form of formula, so it is R of t, U of t equal to A at t greater than or equal to 0. Okay. Otherwise, it is 0. Otherwise, it is 0. Uh, I think Shreya has asked one question, why we are not taking the Laplace of this 1. So we are taking the Laplace, we are taking this unit impulse just for the understanding purpose. Like in practical situation, this impulse is infinite at t equal to 0. Okay, but for just for the sake of understanding, to represent it on the graph, we will be taking the value or the magnitude of this impulse input as 1, and that's why we will be calling as this as a unit impulse response. Now, although we know that for finding out the transfer function, we take the Laplace of all the quantities like input and output. Input and response, we take the Laplace transform because it is easier to solve. So that's why I took the Laplace of this equation just for the sake of what we can say understanding that we will not directly solve this equation with respect to time, which take the form of ordinary differential equation or partial differential equation. So to simplify it, we take the Laplace transform, and this one is just for that we are representing a unit impulse. Okay, so I hope I have made it clear. Going
Yes,
back,
sir.
going back to the step response. So in step response, we have given a command like input signal, and if this A, whatever the A we are calling, if this A is equal to 1, again for the sake of uh, example purpose, it is called as unit step. It is called as unit step. Okay. Now, again, we take the Laplace of this. So, if we take Laplace of this, so it is R of t, which is equal to R of s, which is A upon s. So, for this A, it is A upon s. Or if we want here also, if we want, it may be 1 upon s, or if we take it is A is equal to 1, so it is 1 upon s in this case. Okay, like if we took over here, it is 1. So if we want to take it the complete Laplace transform for this particular thing, it is A of s. Okay, and instead of that, if we are putting a unit step value, it is 1 upon s. But we are not interested in unit step, we are interested in this thing, A of s. So this unit, when it comes into consideration, when we use for it particular testing purpose. So as we said that these are the test input signal. So in that case, when we are giving some known input signal, unit having input signal having magnitude 1, so in that case, we can be considering that as unit impulse input or unit step input likewise. Okay. Next type of input is the ramp input. Now ramp, you might have heard this word. So we use the ramp uh, in various buildings or hospitals for assist the people with disability. So the ramp response, ramp input, not response, ramp input represents a linearly increasing input command. It represents a linearly increasing input command. That is what we call it as a ramp response. Let me represent it on the graph. So it is your r of t, and here you have time. So this is what we call it as a ramp response. It is linearly increasing input command. Okay, we can find out the slope over here. So mathematically it can represent as r of t is equal to a t, where t is greater than or equal to 0. Here your a is the slope of this line, inclined line, and at t is greater than t is less than 0, it is equal to 0. Now again, if a is equal to 1, it is called as unit ramp. When the slope is 1, we call this as a unit ramp input. Now if we take the Laplace of this r of t, which is r of s. So if we take Laplace of this, it will be a upon s square. So this is s, a upon s square. Now in case of unit ramp, it will be, if the slope is 1, it is 1 upon s square. Now when the system is subjected to ramp input, we need to study the system behavior for the linearly increasing functions like velocity. If we cannot increase the velocity at a start at up to certain level, we have to increase the velocity linearly. So whenever the system function or the behavior of a system is linearly increasing function, then we use the when we then we make the system to give a ramp input, or the systems are subjected to the ramp input. Okay, this is ramp input. The fourth one is parabolic input. The fourth input is parabolic input. Now the rate of change of velocity, we know that the rate of change of velocity is an acceleration. Okay, what is an acceleration? It is a rate of change of velocity, and this acceleration is a parabolic function. This acceleration is a parabolic function. It is represented on the diagram like this. This is r of t, this is t, like this. So this is your parabolic function. It is represented as r of t is equal to a by 2 t square at t greater than or equal to 0, and at t less than 0, it is 0. Again, if we say this a is equal to 1, it is called as unit parabola. If this is a is equal to 1, then it is called as unit parabola. We take a Laplace of this r of t. So it is going to be r of s equal to a upon s cube, or when it is a unit parabola, it is 1 upon s cube. The last type of input is sinusoidal input. So sinusoidal input. whenever there are applications which need when there we encounter the varying frequencies, if the frequencies of the input they are varying, and uh, our interest is to study the system with the what is the response of the system with this varying frequency. So when we want to study the frequency response, when we want to study the frequency response where the system, the control system is subjected to varying frequency, so in that case your sinusoidal input are used. The very common example or the very simple example is when we need to check the quality of the speaker of the music system. In this case, we play the different frequencies, the different sinusoidal waves, and we study their attenuation, how these systems are, how that particular music system is responding to the different input frequency, these sinusoidal waves. So it is more inclined toward the frequency response. Okay, so it is given by the formula R is equal to A sine omega t. Okay, so this is what we call is sinusoidal input. But at the first stage, we will be studying the inputs that are the function of time, and we can say that this sinusoidal input is a function of your frequencies. So we'll not discuss this sinusoidal input, or we'll not consider this sinusoidal input for our discussion. When we go for the frequency response analysis, we use this sinusoidal input. Okay, let us summarize the for the time response analysis. What are the test inputs that we are going to discuss. So Laplace, in Laplace domain, and input. So first input is your impulse input. We can say it is 1. Second one, the step input, A upon S. Then we have ramp input, we have A upon S square, and then we have the parabolic input, which is having Laplace A upon S cube. So mostly I think we'll be concentrating on this step input. Okay. Now going back to our discussion, we have considered that your total time response is equal to steady state response plus the transient response. Now let us discuss more about steady state response. Now in this steady state response, as discussed earlier, it is a part of output response where your output signal remains constant. So it is part of output response where the output signal remains constant. You must remember this. Output signal, more or less, it remains constant. Now the parameter that is important in this study is the steady state response, is steady state error. Now we talk of steady state response. We have discussed steady state response. So this portion is called as steady state response. But the parameter which is associated with this steady state response is your steady state error, which is of very important. Okay. In fact, This steady state error is the only thing that the characterizes the steady state response. The steady state response is only characterized by this steady state error. Now, error in general, as I said earlier, it is the difference between input that is desired and the output, what is actual. Now, the steady state error at t tends to infinity, I can write as error steady state if I take the limits t tending towards infinity is an error. Now we'll derive the formula for the steady state error. Do we have time? Okay, let me draw this diagram. So this is a simple system, a feedback control system. So we have a feed forward element, we have a feedback element, we have a comparator over here to which we will be feeding the feedback signal, and over here we have the input signal, and this E of S is your error signal. So R of S is Laplace of input signal R of t, C of S is Laplace of output, B of Laplace of feedback signal, E of S is the Laplace of error signal, Laplace transform of an error signal. Now this is your generalized error. Whatever the error that you are feeding to the controller is the generalized error. That is, it's a difference between input and output. Now this error, you please note that this error is not a steady state error that we are interested in discussion. Okay, so this error is different than that of this steady state error. This one is a generalized error we can talk of. Again, this g of s is the transfer function of the main system, and h of s is the transfer function of the feedback element. Now, what is E of s? So, E of s is equal to R of s minus B of s. Okay, so you are getting me. So, this E of s is equal to R of s minus B of s. But we know that B of s is equal to C of s into H of s. So what is this B of s? It is C of s into H of s that we had discussed, and also C of s is equal to E of s into G of s. C of s is equal to E of s into G of s. So therefore, if we put the value of C of s over here, so B of s is equal to E of s into, or we can say that this is, so this is R of s minus B of s is equal to, we can say that over here we are putting it, it is E of s into G of s into H of s. So if we put over here, okay, and if we took this E of s, therefore this E of s is equal to 1 plus G of s into H of s is equal to R of s. So this we have derived earlier that E of s is equal to R of s upon 1 plus G of s into H of s. So this we have derived. So this equation is the generalized error in your Laplace domain. Now the steady state error that we are interested in, that is occurred at when t tends to infinity. That is after long time your steady state error occurs. That is, I can say ES a steady state limit t tends to infinity, then this error occur. Now this E of t is generalized error. Now when this generalized error, after a long duration of time, we can expect it as a steady state error. So if it remains for a longer duration of time, it is called as steady state error. Let me put it in a simple way. If you are if you want you to be at a certain position at a managerial level, okay, and you are working currently on the supervisor level, fine, and but you put your what we can say, put your efforts, and you achieve that managerial position within 1 year or 2 years duration. So this is this, whatever the error was there, that is a generalized error. But at the retirement age also, you are having supervisor at supervisor's position, not able to achieve the managerial level. So that is called as your steady state error. So for a longer duration of time, if the error is going to exist into that particular system, that is called as your steady state error. Now we'll what is the time? 11:12. So we'll stop over here, but we'll continue our discussion about the steady state error, and we'll discuss it with the help of the